polynomials. Ugh. Polynomials, 3rd degrees, 4th degrees, 5th degrees, 6th degrees, with different terms being added and subtracted. Oh my goodness. It gets messy, it gets gross. But there are some things we can tell. So first of all, we can tell at most how many zeros they can have. At most how many turns they can have. And so the first thing that we try doing is finding zeros. And I told you these are easier ones to start off. Why are they easier? How did we start off this example at the end of yesterday? What was the first thing I did? Yeah, I factored out the GCF, negative 2x squared. Now I didn't finish because I was like dot, 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 hey look, it's not that bad. So let's go ahead and finish right now. So first of all, pulling out the negative 2x squared, what was left again? Good, x squared minus 1. What can I do with x squared minus 1? He's a quadratic. He's not a perfect square. Perfect square would be x minus 1, x minus 1, x plus 1, x plus 1. Who's this guy? What's his name? Difference of squares. He's the difference of two squares. How do I always factor any a squared minus b squared? A plus of square root, right? Square root. Got it. What am I supposed to be finding? And what do zeros mean ever since the Pre-Cal Graphing Calculator Handbook? We'll find the x's when? Who do we set equal to 0? These are the x-intercepts when y equals 0. So we set the whole shabam equal to 0. How do we solve when we have factors equal to 0? We set each and every one equal to 0. So negative 2x squared equals 0. Solve. Guess what? X equals 0. Divide by negative 2. There's 1. X plus 1 equals 0. Most of you can do that mental math. X minus 1 equals 0. Oops. Add 1 to both sides, right? And x equals 1. So how many zeros does this guy have? What was the maximum that this could have? 4. Huh. It could have at most the number of the degree real zeros. So it was a 4th degree polynomial. It could have at most 4, which means, well, that's weird. It only has 3. But that's also weird because it has more than, didn't we see an x fourth is just like an x squared, but a little bit steeper? The most number of zeros it could have in that form. Just 2 or 1 or 0. So how did it get 3? We'll figure that out in a second. What's the maximum number of turning points? Yeah, my degree is 4, right? Remember, whenever we have a polynomial, the degree is the highest power. So we can use that and say, okay, at most 4 zeros and at most 3 turning points. There was something special that happened, though, and that's the reason why we only have 3 zeros and not 4. But something special that happened along the way was that we got this little x squared. Technically, isn't an x squared an x times an x? So aren't there really repeated zeros, 2 different x values that have the same 0? We could have said x times x, negative 2x times x equals 0. So x equals 0 or x equals 0, but either one was the same answer, so all we said was whatever, x equals 0. But if you look at it, we did have 1x, 2x's, 3x's, 4x's, like our degree, just 2 of them shared a 0. Whenever we have repeated zeros, aka x and x both have the same 0, x equals 0, x equals 0, we call the 0 a multiplicity, having a multiplicity. Now it's kind of awkward. We could technically say that negative 1 has a multiplicity of 1. It's awkward because it's not a multiple, right? But 1x, we could call it, what did Mr. Che call it? I say a product of linear pairs. He called it x-intercept form. Is that what he called it last year? There was the ax squared plus bx plus c form. There was the a times x minus h squared plus k form. And then there was the x-intercept form, which was x minus a, x minus b, x minus c. So 1 x-intercept has this 0, multiplicity of 1. 1 x-intercept has this 0, multiplicity of 1. But what am I going to say for this one? 2 x-intercepts have the same 0. I'm going to call this one multiplicity of 2. So there's something special to talk about. Okay, there's something special going on at 0. There's something special going on at 0, but what? Let's keep going. I'm not going to show you the picture of this quite yet, but so far we've figured out there are 3 x-intercepts. We've figured out there are at most 3 different turning points. Let's talk about something else that we can test with this polynomial, this quartic polynomial that's kind of messy. And we've already figured out he can't be a parabola. He can't be. He can't be a parabola and have 3 zeros. As you guys are writing that down, I'm going to write down this function and we'll build up to trying to figure out what this guy looks like. Getting the gist of what he looks like, the general idea. Angelique is gone today. Is anyone else gone? No. Okay. Okay, as you guys are writing that down, up here on the whiteboard, maybe someone can take a picture of this before you leave today to send to Angelique. Up here on the whiteboard, let's talk about what we know. What do we know about end behavior just practicing from like the beginning of section 2.2? What can we say about end behavior of this guy? What's his degree? And that's what kind of number? Oh, I was just looking for even. Sorry, I wasn't meaning to make it hard. Oh, you did? It was just too quiet. Okay, even. So because we have an even degree, what do we know? As x goes to negative infinity? Okay, why'd you say negative infinity, Gavin? Or maybe you didn't. Somebody said it. As x goes to negative infinity, where are the y's going? Okay, think about the picture, right? It's not this one. Why? Okay, so what is it? Okay, so since it's down, okay, as I go to the left, what are my y's doing? Negative infinity. And as I go to the right, what are my y's doing? Oh, that's what you said. Got it. So right away I can say, okay, I don't know much, but I know it's somehow going down and it's going down. True? Okay. Zeros, we just did that. And didn't we figure out the zeros are going to be negative 1, 0, 1 from all of our factoring? So we can come up here and say, okay, sweet, let's make a 0 at negative 1. Let's make a 0 at 0. And let's make a 0 at 1. We know those 3 points for sure. And we know somehow it's going down, it's going down. Maybe some of you have an idea of what this picture looks like, but let's talk about, maximum terms. I forgot that one. What are the maximum number of turns this can have? How can it have 3 turns? We'll figure that one out in a second too. Sign charts. What does this say? Make intervals using the zeros of the function. I want you guys to put in parentheses the zeros and the domain. But what's the domain of any polynomial? How left, how right is any polynomial going to go? Yeah. So what's the farthest left a polynomial can go? Negative infinity. Think the number line. Think the number line that I just marked with a negative 1, a 0, and a 1. If I'm thinking the number line, like the x-axis, if it helps, you can think of this function is going to go forever left, forever right, negative infinity to positive infinity. That's what's going on. This direction and this direction. And we just split it up with negative 1, 0, and 1. I want you to make intervals. of each little piece of the number line. So what's this first piece of the number line going to be? Negative infinity to negative 1. Keep it open. Just like we talked about increasing and decreasing, always keeping open. What's the next interval? Negative 1 to 0. What's the next interval? 0 to 1. The next interval? 1 to infinity. So we're going to split up, and these aren't just x values, so maybe it'd be a little bit better. Maybe I should have done that. Naming this not just x, but naming them x. You guys are going to start to get confused if I put x int. I love shortcutting things, but the problem is, if I shortcut this x int, wouldn't you think x intercepts? Okay, then I'll say x interval instead. Okay. Step number 1, make intervals. Ah, I got them. Step number 2, check the sign of f of x in each interval using test points. Test points? What are test points? Something in between. Something in between. What? Doesn't matter. Any number you want that's in between, just got to plug it in. So we're going to go ahead and test points and figure out the sign of f of x. Is it a positive number or a negative number? We need to plug in 1 for the first, 1 for the second, 1 for the third, and 1 for the fourth. So someone give me, it doesn't matter. It doesn't matter. The only places where f can change from positive to negative are at zeros. And we already have it marked down, the number line marked down with the zeros. So all we're trying to figure out is, okay, if these are our zeros, a sign chart just says, where was the function before this 0? Was it above or was it below? Check the sign. Was it positive or negative? Where is the function in between these two, above or below? Check the sign, positive or negative. Where was it in between, above or below? All I have to do is test 1 point. And it'll tell me the above for the whole function or the below for the whole function in each piece. So, what's any number in between negative infinity and negative 1? Negative 2, sure, that works. What's any number in between negative 1 and 0? Sure, negative 0.5, that works. Negative 1/2. What's any number in between 0 and 1? Sure, but it could have also been 1/3, 1/4, 1/5, 7/8. It could be anything you want it to be. 0.9, sure. What's any number in between 1 and infinity? These are the most commonly picked, but did you have to pick those ones? No, just any number inside each interval. What happens when you plug in negative? Any mental mathers out there helping us out? Pause. In your brain, do you think it's easier to plug in? Just curious. I have what I would guess, what I would think, but maybe you guys disagree. What do you think would be easier to plug into, the original function over here or the factored form? I think so. Some of you get scared plugging into the 4th power. Doesn't mean you should, but you do. So maybe it's easier to plug into the factored form, especially if we only care about the sign. We don't even care about the number, although we'll write the number down. Plugging in negative 2, I'm going to plug it into this one. Negative 2 times negative 2 squared. Negative 2 minus 1. I like this math a lot easier than the other. Doesn't mean everyone agrees with me. That's okay. You could plug it into the original. I'm just plugging it into the factored. Because then I get this little, oh, it's a 4. Oh, it's a negative 8. Oh, it's a positive 8. Oh, it's a negative 24. Double check my math. Let me give you 60 seconds to get ahead. That way I can come behind and you guys know whether or not I've done good mental math or bad mental math. Keep plugging in. Keep plugging in, Robbie. Plug it in, plug it in. Practice your mental math skills. You can figure out which one you think would be smarter now before homework, smarter to plug in. The factored one or the original one? Both work. Both should give the same answer. This idea of using a sign chart is what the book would say. I forget how they put it. Finding other strategic points. How else could they put it? Finding other test points. Yeah, Gavin. Mm-hmm. Oh, don't worry. When we get the picture, when we get the graph of this guy, I'll explain the multiplicity a little bit more, because he actually has a clue built into him. I just haven't really explained it yet. But right now, just for right now, you only have x to the 1, it's a multiplicity of 1. You only have x to the 1, it's a multiplicity of 1. You have x squared, both getting to the same answer, it's a multiplicity of 2. So, kind of, yeah. Think about your original x, and there were 4 different x's, like x, 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 being multiplied to get this 4th degree, with extra stuff going on. So ultimately, each of those x's could have had a 0. So there are, in a sense, 4 zeros here, just one was 2 for 1. Multiplicity of 2. Robbie? Yeah. Oh, because whenever I factor out the GCF, I'm really dividing. So when I divide by negative 2x squared, the negative 2's are 1. X to the 4th over x squared is x squared remaining. But when I divide this guy by a negative 2x squared, everything reduced, but a positive over a negative is a negative 1. And remember, when you reduce it, like 5 over 5, 2x squared over 2x squared, there's always a 1 left. We're not canceling it to 0, we're reducing it to 1. All right, do you guys agree with my negative 24? Did anybody figure out that this is down here? But in this one, it's going to be a positive 24, right? I think there's some symmetry to this guy. Plugging in a negative 1/2. Negative 1/2 plus 1 is 1/2. Negative 1/2 minus 1 is negative 3/2. Let's see. I see these little 2's reducing, the 2 and 1/2. I see a negative times a negative being a positive times a positive is also a positive. So I see 1/2 squared is 1/4. 1/4 times 3/2. Anybody get 3/8? I see one head nod. Uh-oh. I lose some of you guys in the fractions. 2 head nods. What's going to happen if this changes to become a positive 1/2? Positive 1/2 plus 1 is 3/2. Positive 1/2 minus 1 is negative 1/2. Guess what? A negative times a negative is still a positive. These 2's still end up reducing, and I still get the exact same thing. I think it's still a 3/8. So I end up with a negative 24, a positive 3/8, a positive 3/8, and then a, wait a minute. Did I do this wrong? Negative 2, 2 squared. Negative 2. 2 plus 1 is 3. Yeah, it's a positive, right? Doesn't make sense if it's a positive. Oh, it's a positive 1. That's funny. Okay, go team. See, that's why I had you go ahead. Thank you. So what can I do to my graph now? Can't I actually mark other points now? Not just my zeros. Can't I go to negative 2 and not just stick with negative 1? And can't I go to positive 2 and can't I go to positive 1/2 and negative 1/2? Negative 2 is way down here. Negative 1/2 is barely up there. 1/2 is barely up there. And 2 is way down there. If we just guesstimate, going from negative infinity, because I know the end behavior, coming up through the 0, going through, Does this make sense? Does it look almost like a parabola? Almost, but what was funny in between? There was an extra 0, which means there were some smooth turns going on. But how many smooth turns were there? We had a maximum of 3, but how many were there actually? 1 smooth turn? Oh, how many were there? There were 3. Increasing to decreasing, decreasing to increasing, increasing to decreasing. There are my 3 turns, 1 and a 2 and a 3. It had 3 turns, it had 3 zeros. But wait a minute, multiplicity, I still don't get it. What was so special about the 0? What's special about the 0? if you have a W graph, why could there be up to 4 zeros? Couldn't the x-axis have hit right there? If it hit right there, wouldn't each and every branch have had a 0? But what happens when you have a multiplicity? 2 branches come together at the same 0. Gavin, multiplicity of 2 means 2 branches are joined in the exact same 0. So this little 0 actually indicates 2 branches, not just 1. So that was something a little bit special with multiplicity. And I think, do I remember? Oh, hey, did you guys sketch the graph yet? If not, let's do so. Probably a lot of you guys did, but not all of you might have. Oh, I didn't want the page. Undo. I just wanted to delete you. So what did we do? We put it all together. We said, okay, from this guy, who factored down to be the negative 2x squared x plus 1 times x minus 1, we were able to know at negative 1 there was a 0. At 0 there was a 0. At positive 1 there was a 0. Because of our strategic sign chart, we were able to say, hey, let's go to negative 2 because getting a point in this part of the interval is helpful. We figured out negative 24, aka not only is the function below, coming from below, but also we got a specific point. We got negative 2, negative 24. We had something similar with negative 1/2, and we got negative 1/2, 3/8. We figured out positive 1/2 is also 3/8. This is probably a little bit stretched, a little bit distorted, because negative 24 should be way lower, 3/8 should be way lower. Just trying to make it super, super clear. And then we got 2 to be negative 24 also. And we used our knowledge of polynomials making smooth turns. We knew this guy has an end behavior of negative infinity, so this made sense that it's going down and continuing to go down. We knew that because of our sign chart, there's not a 0 until negative 1, so this couldn't have gone above and then come back down. It had to go straight up, increasing to the 0. It's going to keep increasing. It's going to hit the top of its motion somewhere in here. Maybe it's negative 1/2, maybe it's somewhere else. But for right now, we'll do the best we can, which is stopping at negative 1/2 and then going down to the other 0. Smooth polynomial, going up and then going back down. This seemed to fit the pattern of it being almost like a parabola, but a little distorted in between because of these little extra negatives and the plus with the extra term in there. And then we talked about how, because of the multiplicity at 2, or of 2, at x equals 0, it kind of makes sense that each of these branches, the decreasing one and the increasing one, sharing a 0 is going to bounce off. Hey, that's actually a clue that you can always use. Multiplicity, let's talk about that. There's a clue. Oh, that's awful. I apologize. That's disgusting and gross. Hold on. Give me a sec. It was something. Not sure if it was a good something. Multiplicity. There's a clue, a graphing clue, which is really nice, actually. There's a graphing clue. Let me pull that down just a little bit more. That has to do with multiplicity. If multiplicity is odd, whether it's 1 or 3 or 5, if multiplicity is odd, now careful, multiplicities are only of 0. So you might want to put multiplicities are of 0s or of the x-intercepts only. When factors are repeated to a power of k. So Gavin, what you were saying with the power does work, but you can't always see it inside. Sometimes the whole factor is raised to a power. So in our example, we could have actually rewritten this as negative 2x minus 0 squared. So that's kind of how also we could have seen the multiplicity if we had rewritten this. That would be to the 1, that would be to the 1, and this would be to the 2 multiplicity. But the multiplicity is whatever power the factor is being raised to. But here's the dealio. If that number is an odd number, 1, 3, 5, 7, we're going to cross through at that 0. At that 0, the graph is going to cross through. It's going to go from below to above or above to below. And if you guys check out your graph, look at this guy. At -1, didn't he cross through? He went from below to above. And at 1, he crossed through from above to below. So whenever the multiplicity is odd, the graph, when it goes to that 0, is just going to cross through it. But here's a cool trick. Whenever the multiplicity is even, when you come to an even, it's going to bounce off. What I mean when it gets to that 0, it's going to bounce off. It's going to return in the same direction it came from, like you see here. It bounced off. Now, it didn't bounce off in a sharp point because all polynomials need smooth turns, but it did have to go ahead, come down, and then bounce back up. So odd multiplicity, graphing clue, always going to cross through for polynomials. Even multiplicity, always going to bounce off. So, just because homework problems can get kind of messy and the wording might be a little different than I say in class, I wrote out an example, number 75, just like the one in the book, or the ones in the book that put all of these ideas together. This is the wording that the homework problem is going to have. And so maybe, it'll be helpful for you guys to do one using the directions in the book and seeing how what we've done today in class is exactly what you need to do this problem. You ready? Okay, here we go. Let me zoom in. I want you guys to check out the directions. Take a little bit of time. Because tonight when you're doing homework, this afternoon when you're doing homework, in a study hall when you're doing homework, I don't want to just tell you the answers. I want you to struggle just a little bit, just like you would if you got to this in homework. According to the book, it says to basically lead up to a sketch by, number 1, applying the leading coefficient test. That's their wording. I'll explain in a second how I would interpret that. But for right now, applying the leading coefficient test. That's their step 1. Step 2, find the real zeros. Step 3, plot sufficient solution points. What? And then step 4, drawing a continuous curve through the point. Continuous, no breaks, no holes, no jumps, smooth turns only. Continuous curve through the points. Can anybody tell from the 4? Wait. Huh. Oh, well, hold on. Maybe one of mine is additional, not necessary. Out of the 4 up there, 3 of them apply directly to A and B and C. One of them is just kind of like an extra little FYI. 3 of them apply to the A and B and C because D says put it all together. Can anybody figure out which of those 4 up on the board have to do with the leading coefficient test? Kyle, and behavior. Doesn't leading coefficient say, look at the guy with the highest degree and look at his coefficient as to whether he's positive or negative? That's talking about end behavior. From that leading coefficient, we can tell the end behavior, what's going on to the right, to the left. Which of those ones up there have to do with finding real zeros? Yeah, that's kind of silly, I suppose. Zeros. So then what does C mean? Plotting sufficient solution points. Sign chart is where we strategically found a few more points. Pause. Give everyone in your group a high 10, not a high 5. Let's get more exciting than that. People are falling asleep and it's a struggle. It's kind of warm in here. Keep going, keep going. Everyone in your group needs a high 10. Pat them on the back if they're falling asleep. Be like, come on, we got this. All right, here we go. This is the one where a lot of people get stuck in homework, but we got this. If I could have you jog it out, take a lap, I would, but I can't. I mean, we could, but you might get hurt. All right, you ready? Letter A. So how do we answer leading coefficient test? Okay, how do we answer end behavior? Right? This can be your answer to end behavior. Is this what the back of the book's going to do? I don't know. We'll talk about it in a second. But this is how I'm showing you. Ooh, this is one of those you can't just copy what CalcChat has because I'm asking you to do it a very particular way. Oh, snap. Doggity dog. All right, so diggity dog. What does x going to negative infinity? Hold on, pause. That's confusing. Think about the picture. Okay, he's odd, so what's going on? Opposite. Is he a positive odd or a negative odd? So which one's right? Positive, always going up. Ooh, hey, that's nice. Negative, always going down. Anyway, positive, always going up. So what's going on as x goes to negative infinity? Is that to the left or to the right? X going to negative infinity, that's to the left. What's f doing? So then what would you guys answer for x going to positive infinity, aka leaning to the right? And if we want, can't you do little arrows for yourselves and be like, oh, hey, by the way, doesn't that mean that it's going to be one of like these guys? Is that okay? I don't know how. He could connect like this. He could connect like this. I don't know. I don't know how he's connected, but somehow he's starting from negative infinity and going to positive infinity as far as the y's. All right, letter A, dun, 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 dun. Letter B. Finding the zeros, we set the whole thing equal to 0, and what do we think about first? Are there any? Starts with a G and ends with a CFs. GCFs. Yeah, who can I pull out? X. And are you guys in honors okay to think that it'd be x squared minus 25, which is x minus 5, x plus 5? So what are my zeros? Gavin, what are their multiplicities? Yes. 1 and? See it? Oh, yeah. No. Come down here to the factored form. Because once we have it in factored form, it shows us each of our zeros, right? And then look at each zero. Each one just has, so we have multiplicity of 1. Hey, graph clue. So what does that mean about each of those zeros on the number line? What's the graph going to do? Just cross through, right? It's not going to bounce. Cross through. One branch per zero, crossing through. So we can even put cross through if that helps you guys for your visualization. What's the last step? Plotting sufficient solution points. Table. I know you might not like my table. You won't even see the table necessarily in CalcChat. But here's the problem. It's really, really helpful in preparing you for sign charts in calculus. They're of a little bit different information, but the idea is so similar. What intervals are we going to mark down, guys? Think of your number line being split up by your zeros. Think of the x-axis or a number line being split up by the zeros. What intervals can I write for each piece? Good. How left does this piece go? Negative infinity. How right does this piece go? Negative 5. Do you guys see it? There's one piece. What's the next piece going to be? Negative 5 to 0. What's the next piece going to be? Struggle. I didn't leave enough room for myself today. So I have negative 5 to 0. I have 0 to 5. And what's my last one? Perfect. Perfecto. What do I need to do at least once in each of those intervals? That's my plotting sufficient solution points. Yeah, plug it in. So I'm going to have f of how many times? I think I have 4 intervals, right? So what could we plug in? I don't know. You guys feeling like negative 6? We could go halfway between negative 5 and 0 if you really, really want, but we could also cheat and say, oh, we only have to do 1. So how about negative 2? Then 2, then 6. I don't want to do negative 2.5. We're just doing as best we can. The general idea, the gist, let's not plug in decimals. Bye, Adam. It's up to you guys again. I know what I want to do, but I'll ask you, do you want to plug into the original where you have to do x cubed minus 25 times x, or do you want to do the factored? Which one? Original or factored? Okay, yeah, I'm going to do factored too. If you want to plug into the original, which isn't horrible, right? 6 times 6 times 6. You can do 2-column multiplication, or you could just plug in and say, oh, it's negative 6 times negative 6 minus 5 is negative 11. Negative 6 plus 5 is negative 1. Maybe that math is easier than cubing negative 6. I like plugging into factored, but you can do the other if you have really good mental math. But we do end up with a negative 66. Whew, it's down there, huh? F of negative 2. Negative 2 times negative 2 minus 5 is negative 7. Negative 2 plus 5 is 3. Anybody with me on that? I think that's 42. Double check me though. That look good? 42, which is a positive. We're answering the sign question. Negative, positive. Plugging in 2. 2 times negative 3 and 7. I think that's negative 42. And then plugging in 6, which is 6 minus 5 and 6 plus 5. I think that's 66, a positive. Could we graph all of these points? Yeah. Do you want to necessarily make your graph to have a negative 66 and a positive 42 and a negative 42? Maybe not. But can you guys figure out how we should be able to get the gist of the graph? The gist of the graph is you have zeros at negative 5, 0, positive 5. At negative 6, you're going to be way down low. Coming from, right, negative infinity. Then at negative 2, you're going to be way, now this is really zoomed out. This is not zoom standard at all. At negative 2, you're going to be up pretty high. At positive 2, you're going to be down pretty low. And at positive 6, you're going to be up really high. Now, if you connected with our points, guess what? You would be just a little bit off because you didn't do negative 2.5. And I think actually the max isn't even exactly negative 2.5. If you guys put it in your calculator, I think it's a little bit more wonky than that. Actually, I could figure it out real fast. Hold on. It's going to be at negative 3 minus 25. Which, it's going to end up being negative 3x squared. What? 25? Negative 3 plus or minus the square root of 25 thirds. Which would be, don't ask me where I got it from, just nod your head that it works. 25 over 3 is going to be 8, 8 and a little bit, 8 and a little bit square rooted is a little bit less than 3. It's going to be like 2.7-ish, 2.8. Go in your calculator and figure it out. That was the exact plus or minus square root of 25 over 3. Long story short, any of our picking of points doesn't perfectly get it, but do we have the gist? Yeah. Is it a good gist? Yeah, it's a really good one. Just by taking our zeros, taking our like, hey, crossing through, and taking our points to say, hey, let's go, let's go, let's go, and there we go. It's good enough. Austin. No, you could, well, it has to be a number in here. So it could have been negative 7. I'm lazy, so I picked the smallest one possible. This one could have been like a negative 1, so you could have actually hit here. And you still, like, you would have been off, but so was negative 2. Like, you could have picked negative 3 or negative 4. It just has to be something in between, and that's a good enough gist for me. Is that cool? Cool. So, our last thing of today. Yeah. Our last thing of today, he has 2 pages. One's an example page and one's like a note page. Intermediate value theorem. Oh well, we won't start 2-3 today, but that's okay, guys. We're finishing 2-2. And you guys will be more than prepared. We're prepared enough for homework. Let me give you a second. Intermediate value theorem. We've actually kind of talked about it, I think, at least once this year. Ironically enough, calculus talked about it too. It's pretty important. In calculus. You guys are just getting like a little baby snippet of it, but it's basically the same thing that calculus learned. There is a height example I'll give to you guys in just 1 second. But one application, a key application that you guys are going to be using, has to do with guaranteeing zeros. Because what if the factoring doesn't get you nice zeros? What if you can't factor it? And there's just one example here. We're going to definitely get into synthetic division, long division, factoring more than we can even now with GCFs. But I'm going to show you the general idea of what's going on with my calculator. So if you guys have a calculator, at least one per group, grab it out. I want you to put this function in the Y1. And as you guys are looking at these examples, it says table step, table step, table step. Oh, stink, table step. That's a thing we've done before, right? Try to find the table setup menu. Hint, look at the window button, look above it. There are ways to change up our table setup. But it doesn't call it table step in the calculator. What does it actually call it? Delta table. Change in table. So when I say table step, I'm showing you the delta table or the change in the table. That means if you have your function, which is the one that they gave us, x to the fourth minus 10x squared plus 3, and you go to second window, go back to automatic if you have ask. We did ask at one point. Change in table 1, or we could change it to 0.1 or 0.01. There's actually a shortcut to that. Let's go look at our table. If we're looking for zeros of a function and the factoring didn't cut it, because if you guys look at this, there's no GCF, and even if you do the x method, thinking about 3 and 10, because there's no x cubed term, there's no x term, you could almost do a trinomial on this. X squared plus something, x squared minus something. No factors of 3 make 10, so even if you tried to do that, these factors are not pretty. Look at the table, though. Can you tell there has to be a 0 between 0 and 1? How can I tell that? Can you tell that? Why? That's intermediate value theorem. If the polynomial smoothly connects points, if it went from a positive to a negative, what did it have to do somewhere in between? If a continuous function goes from a positive to a negative, what has to be somewhere in between? A 0. Or if it goes from negative to positive, what has to happen somewhere in between? A 0. Here's the height example. If when I was born, I was, I actually don't remember how many inches I was. Let's say 22 inches. I was a really heavy baby, but we'll just say 22 inches. Okay? If I was 22 inches when I was born and I'm 6'2", did I used to be, yes, even me, 4'8" at one point? How about 5'2"? 5'10"? 5'11", 5'12", 6 foot, 6'1". Yeah, I was all of those. Why? Because I was a little baby once and now I'm 6'2", and height is continuous. I had to go through all the heights at some point. Do you know when? No. Do I know when? Probably not. But did I hit them? Yes. So if you go from a positive to a negative or a negative to a positive, guess what has to happen in between? A 0. Where? I don't know. Look, change the little plus sign. Let's get even more precise. Let's go by 0.1s. Now I know it's not just between 0 and 1. I know it's between 0.5 and 0.6. Whoa, I'm so much better now. How can I make an even better estimate? Let me go down to this one first of all, and then let me do a plus sign again. I don't want to go by 0.1s anymore. I want to go by 0.01s. I don't think I went by 0.01s. Did you guys go by 0.01? 0.01. Go. There we go. Now I don't just know it's between 0.5 and 0.6. I know it's between 0.55 and 0.56. Do you see what I'm doing? I'm figuring out the 0 without even using, okay, what's the other way to use a graphing calculator to find zeros? Not just looking at tables and figuring out, hey, it's in between, hey, it's in between, hey, it's in between, but to actually use the 0 feature. But what's the intermediate value theorem say? If you see a sign change of a polynomial, you know there has to be a 0 in between. And why is that going to be helpful for us at some point in time? Because if we get to nasty polynomials that we have to try to factor by hand, and there are all these different options to try, we'll say, let me plug in some numbers and find a sign change. Ha-ha, I found you. You're somewhere in there. I'm going to keep looking right there and forget all the rest. All right, cool kids, intermediate value theorem. I think there's like 1 or 2 problems on it. You guys got this. Bust it out for tomorrow. I'll see you later.